Thank you for the grant and the interview. I'm currently I'm an assistant professor in mechanical aerospace and biomedical engineering and optical engineering, and then and that was started at in 2022 fall, so it's closing up to my second year here, and then um, I'm mostly working on semiconductor cooling, and this is a part where we know people are making higher, like highly compact, high performance processors, and those can be very challenging for thermal management. Because we know your cell phone got hot, your computer got hot, everything got hot. When you got hot, you got the reliability issues. You also have the performance throttling. So, and now they are going crazier to stack all the CPU together. So that's what they are trying to do, right? So that makes things very tricky. And one of the biggest challenge is when you stack things together, you don't even know the temperature that's happening inside of it, right? And your chips is very valuable real estate because you don't want to put some sensors inside of that because that could be millions of transistors there otherwise. So what we are trying to do is really leverage the AI capability to better predict what's happening inside of this package. If you stack 4 or 5 chips together, when they simultaneously operate and then generate heat, how can we know where is the hottest spot? And how can we know that this is the time we should slow down so we don't burn the chips? Yeah. Yeah, so this is a collaboration between me from mechanical engineering and Professor Haochen Li from civil engineering. So that's a CEE and maybe and then the title, let me make sure I didn't got it wrong, is real-time 3D temperature profiling in higher dimensional microchips with physics-informed machine learning. Yeah, so basically, computer chips are hotter. They are pretty hot for microelectronics, your phone, your computers. And now they want to make it more compact, which will be even hotter. And we want to use AI to understand what happens within the chips, what's the temperature within the chips to better control and design and operate those.
And so, what motivated you to try and tackle this issue?
So this is, I think it really is when I was looking at some workshop materials from in DARPA or even semiconductor companies, they are stacking things in a unfathomable way. They just like stack things together. All things looks crazy to typical thermal engineering. Um, and so what we look at is it's promising for the electrical engineering because you can connect things really close. Even the new MacBook, they actually didn't stack things together, but put the RAM and CPU all very close, and that makes things really fast and more efficient. But when you actually stack them together, the Wikipedia page just looks crazy for our thermal engineers. So that's why we are really interested in how to address the problem because uh, that's going to be actually that's the biggest limitation if you want to continue to improve the performance.
And so, would you say that that is the main challenge in trying to solve this issue, or is there another issue that is a bigger challenge?
I think from the background, like the motivation part, understanding the internal temperature, really what happens in it, because you can't see the internal temperature. You can use a infrared camera to see on the surface, but nothing in between. Or very sparsely, you may have a sensor or two. I think that's the challenge. The technical part is you only have limited data. You cannot say probe 10 different sensors in a computer chip, which is actually much smaller than what you bought. It looks like this big, inch by inch, but actually the chip is much smaller, like millimeter by millimeter. So it's very hard to distinguish those just using typical sensor. So and there are so many different variables and parameters. And by nature, this is a complicated problem. And what we want to do is use as limited data as possible to get as more comprehensive um, uh, temperature profile. So that's by itself is going to be a challenging process. Yeah, I think this is a quite unique project that it has the benefits of both. Academic wise, people are still trying to explore, especially under these complicated structures, how the AI can actually performs with all the state of art or even improved algorithm, and choosing where to put it there. But this is also have very close relation connection with industry applications. For example, like just computer chip manufacturing, Intel, IBM, or even Apple. So this can, in that case, if you have a better computer chips that makes your phone goes much faster, I think that's also a quite close way to the general like comfort of life or benefits to the um, social society part.
So do you think about this in, I know you're thinking in terms of making the chip more efficient, or, that it doesn't heat up so that more can be stacked, or, so, but do you also think in terms of climate change or those type of things? Like, so as you're saying, it's getting
Yeah.
crazy, too much stacking going on. I know a lot of offshore data warehouses are created. So in the US, it doesn't matter, but somewhere else it matters what's happening to the quality of life there.
Yeah.
So I think this, can you talk a little bit about how this impacts that?
Yeah, so that's a very great point. Because before, when I was working microelectronics, um, that cooling is the cooling by itself. Building cooling is another sector, like you try to reduce the energy. But now with data centers, they are basically combined together. So the data center cooling power is actually a few percent of the US total energy electricity consumption. And it's not going down anytime soon. So everything is just goes up. So in that case, yeah, this is actually in some point become an energy problem.
Right.
Because the majority, more than half of the data center energy consumption
Yes.
is actually with cooling. So that's a big portion of that. So with more like even 5G, or who knows if there's a 6G or not, but even 5G's cooling is also a big issue as well. The other things, the electric vehicles,
Yeah.
we talk about battery cooling, but there's even a trickier part that's called power electronics, that you are using one chip to go through 600 volts and 20 amp. So that one chip may consume more energy than your fridge plus your air conditioning.
Wow.
So so in that case, this is also in a wide range of applications.
Yeah, so if the chip is efficient, so your work is about making the chip more efficient in cooling, or is it about storing more data on the chip?
So this is the great beautiful part of this. So if you make the chip cooler,
Yeah.
right, if you know where the temperature is, you can effectively cool that local region, so you don't use as much coolant. You can make the chip cooler. When you make it cooler, the chips can performs better, and then more efficient, so you will use less power.
Yeah.
And when you use less power and you can cool it more efficient, the water, like for example, you are doing the liquid cooling, the pumping is the majority of the cooling power comes from. So you can use less pumping,
Yes.
and then you can make it more efficient. So you're doing double the work.
Right.
You gain double the benefits.
You're getting bang for your buck, double the bang for
Yeah.
your buck. Yeah.
Yeah, so I think really everybody's life is heavily associated with electronics nowadays, and how to make electronics more reliable, more economical, viable, and higher performance helps everybody to get like make the technology improve and make everybody's life a lot better.
Do you think it would also make our devices even smaller?
Yeah,
Right?
again, this is not directly the impact what
Right.
we're trying to do, but if we have a better solution to make it cooler, that's definitely the case. And I think this is also where there's a lot of potential, entrepreneurship and also startup company and technology development, because everything's quite new, and even the circuit design people are not exactly sure what's going to be like in 5 years. So it's a very exploratory domain.
Right.
Needs a lot of companies and also industries and academia efforts.
Yeah, and I think, one of the things, at least just recently in last month or so, that I've been reading about EVs is that the time it takes to charge and the location to find them. I think that cutting that time or making it portable, I think this could impact both things, right? Like it makes it efficient, but
Yeah,
it also makes it smaller.
one of the key things about EV charging, the reason you cannot charge as fast,
Yeah.
voltage is one thing, but mainly is the heat. If
Yeah.
you charge too fast, you have to go through all the current through the chip power electronics,
Yeah.
and that is the bottleneck. If you charge it too fast, then you create too much heat. Then you may it's a lot of time is limited by that.
Right. Yeah. That's very, very fascinating. Yeah.
Yeah, I think AI, one of the biggest risks is similar to traditional numerical simulation or different ways, is they in many of the cases they will give you a number. But how reliable is that number? What's the uncertainty of that number? How much trust I should put in that number? That is the key challenge of that. Right. I think that's where we need to understand better what that number indicates. Is it? Yeah, I think it's mostly the uncertainty and the confidence level of any AI algorithm is as important as the capability that it can do.
Yeah. So trusting what you get from it.
Yeah, or in the case of understand how untrustworthy the AI is.
Yeah.
Right.
Yeah.
So
like being aware of that. Like what is the margin of error here?
Yeah.
Okay. And then what does that mean? Let's say in terms of your chip and the data that you get and the number that you get. What if it is, if you trust it and it's not correct, what are the directions it could go in?
So I think the challenge is if they speak out a number and you think that's reliable, but if there's an uncertainty range, the upper limit of that uncertainty range, if it's over, for example, if it's over the threshold operation of the chip, you may prematurely, for example, create fatigue, because every 1 degree C, I forgot the number actually. I think every 5 degree C, you basically, if you can reduce the operation temperature by 5 degrees C, you double the lifetime of a chip.
Okay.
So that's why the uncertainty is very important, because you really want to be conservative for the thermodynamic part.
Right. So if you're on one side, you're unnecessarily removing what could have worked for longer. But if you're on the other side, it could damage some things, right?
Yeah.
Because if it's wrong in predicting if it's hot or not, then that would be actually very bad.
Yeah. And that's especially challenging for let's say data centers where you pack everything really tight together. So if it's just operating occasionally, a little bit spike doesn't matter. But if you're operating continuous 24 hours, then the heat accumulates.
Yeah. And so what can you elaborate that on that? Because you're the expert in it. So let's say if it's higher, and so if it's lower, then we are talking about if like money, right? Like we're using extra resources to refurnish what we didn't need to remove. But if it's too high, can you extrapolate on that? Like what are the potential issues or risks associated with it predicting it wrong or breaking down? Let's say the system breaks down in the EV charging example or any examples, if it breaks down.
So yeah, so when electric and the heat intersect, that usually go to a downward spiral, where if you have a electrical heating mechanism where you create too much heat and accumulate too much heat, right? Generally your electrical conductivity goes down as well. So you are likely to create a more concentrated heat.
Yeah.
And that will create the thermal stress. And then when you create a bigger thermal stress, the layer like the layer structures or the contact is supposed to be good, it become delaminate or have like even microscopic change. This will again make the thermal contact even worse. So again, from making electrical worse, now you go back and make thermal worse, and that's the continued downward spiral. So that's why all the computer chips or phone, you see, once it hit a certain, if you expose your sun in your vehicle and you forgot to take it out in the summer in Tennessee, next time you come back, you see the phone doesn't work. You need to cool down before you can work it again. That's exactly, the safety mechanism that
that's the contingency plan. Yeah. My phone, I have a flip phone, and it is so sensitive to heat. I don't like that feature of it. It is so sensitive. It'll just give me a message, cannot work, cannot charge because I'm too hot, or even too cold actually. It will both ways. It needs to be in the range of temperature, which is inconvenient sometimes, but
So you mean if the work is not done, then
yeah.
what's the industry? I think that is part where people are pushing for more high performance computer chips and electronics. If we don't focus on the thermal management, we may end up spend a lot of money, taxpayer money, on the development of the chip, but turn out the benefits you get, the so-called electrical benefits you get and performance can never be realized. That's like you spend double the money for a higher end phone, turn out it doesn't work half the time as well because it's all because of thermal problem. So I think that's the main issue. And we kind of want that to happen as like the research to thermal research to kick off as early as possible, so that when people are designing the overall electric circuits or the semiconductors, they have the thermal part in mind. So otherwise it might be too late when you already have the architecture established.
So the thermal is prepared to meet the demands of the stacking and everything that's going on, right? Yeah.
I think it really is when we have an AI that's working in place, we want to understand how things works. That's why we are building the model, but also trying to see the uncertainties of that, how sensitive it is to a certain different parameters, how sensitive is the result to the parameters. If we have for example, within the package, there's so many different hundreds of parameters. If we know when they do the fabrication, they kind of know the uncertainty of each parameters. So if we can translate those uncertainties to the AI results or through the AI model, then in this case, we have a more accurate results with that. I think that's what we are working on first is sensitivity, and also looking at a joint method, different method to look at this. And I think there's another one, 11.
Yeah.
It's more efficient. Yeah, I think what exactly is it supposed to look? Did I answer that 11 already?
My set is a little bit revised, so what do you have for 11?
Okay.
What is the question you
I
have?
think,
Yeah.
yeah, what exactly is it that your AI related research is supposed to make possible, easier, more efficient? Yeah, I think that's
Yeah,
just like
yeah.
a
So
thermal management.
yeah, please respond to that. Yes.
Yeah, I think really the research focus on thermal management and better reliability of electronics. That's and we want to make those more energy efficient, promote faster, and benefits our like not only daily life but all the other convenient technology convenience we are enjoying now.
Yeah, I think this is quite foundational. I mean, looking at the title, I didn't really understand, but I'm absolutely enjoying our conversation, getting to learn more about it. And I think, there is definitely more outward projections of quality of life implications of your project, because it's really going in the right direction of reducing that heat, reducing that electricity use, and making it, more efficient, making devices smaller and so forth. So I think there's a lot of implications of it, which can be extrapolated by somebody who looks, because you're focused on the really deep technical part, but someone who is more, like the PR person for this grant could be talking about a lot more important implications of this. So social justice. So the next thing we have is, well, the other question was, does your AI Tennessee project have any bearing on matters of social justice? If yes, what are they? Are you thinking about those concerns in design or planning of your tool?
I don't think we have much you mean social concerns. I don't think this is really beneficial to that. So I think it's pretty straightforward technology development to enhance the the current technology, I think. No, I think these questions are pretty good. Everything is very comprehensive. I really enjoyed the interview.
Good. I hope this gave you, because, one of the reasons we want to do this is to bring, technical people and everybody sort of this awareness of what are the social implications, what are the quality of life implications. And I think your answers are really helpful in understanding that. And thank you so much for your time.
Thank you very much.